So what we have here is our Schmitt trigger, right? And what normally you would have is some kind of signal, right? Which then, and you would have this noise, right? Which then you would get a combined, I'm trying to show like a sine wave that's noisy, right? And because this is an inverting Schmitt trigger, what you would get out is something low, high, let's see, low, high, low, high. And the thing is the Schmitt trigger can actually filter out worse noise than this, where if I'm high and I'm bouncing like that, oops, as long as I don't go below the trigger point, that'll just stay low, right? And this is the hysteresis plot where in between here is the hysteresis. And in time, what's going on is if the output is high, the voltage has to go to this trip point, and we can just call it trip high to low, and then it'll go down. So the input can bounce around between here and it won't change state. But if it's in this state, right, it's got to go all the way here before it changes state, right? And this hysteresis width is kind of important. Now, rather than putting in a sine wave, this research puts in a noise signal here, all right? And, looks like something like that. Now, there's a few ways we could describe this signal. In some papers, you see this range, right? They call that the density. But in this paper, it's called something called root mean square. And the equation for that is 1 over the period integrated over the whole period. Xt is the signal in question, and you square it, and it's all done with respect to t, and you take the square root. All right. So now RMS value, in the circuits course, we go over this calculation for things like square waves, triangle waves, and other such things. Now the noise is kind of random, right? And so you don't really know how to integrate it, right? And what you do is you just numerically square everything, sum it up, and divide it by the number of points. So here's LT spice, and here's a noise signal. All right. And it does go between plus or minus 500. And we can zoom in, and you can see what's going on. Now, that plus or minus 500 sorry, I'm looking for my smooth draw. okay? So for the one we'll be using, the width is about 0.9 volts, right? And so our noise is going a little bit beyond that. But the thing that we really do is do RMS. And the way to calculate that in LT-Spice is you press Control left click, and it gives you a value of RMS 234 millivolts. Okay, that's a good question. And I'll just take a brief moment to answer it. So what this circuit does is when it runs, it outputs the spice, this output and this output as a wave file, right? And it also reads in this noise file here, right? Which was actually generated in LT-Spice previously. Now Scopy can read all these files, but that noise file in particular we're going to use later, and you'll see that it can read in. So Scopy can read and write LT-Spice data files. So if you measured something in Scopy, you can import it in LT-Spice. If you simulated something in LT-Spice, you can import it into Scopy. All right, but not directly in each tool. You have to save it and load it in and things like that. All right. Now, what I wanted to show you about is, so there's not an analytical solution for this noise. You just numerically find it. All right. But that RMS, you can just find by Control L kicking RMS. Now you could read this into Python, and you can calculate it that way too. All right. Now, let's see what the output looks like. So this is the output of a sine wave of the Schmitt trigger with this sine wave that we're trying to detect, right? And it looks somewhat regular in time. And we can see how regular in time by going View, Fast Fourier Transform. And we can see a peak here at, was it 63, 64 hertz? Okay, 63. All right. Now, that peak is pretty easy to see here, but it's even more obvious when you look at it on a linear scale. All right. And so this is the amplitude of the sine wave coming out. Now that sine wave, yes, it's buried inside this square wave. But what it's saying is the most important frequency in that blue area is in fact the 63 hertz. Now, this doesn't look like a sine wave by any stretch of the imagination, but when you decompose it into a fast Fourier transform, right, putting it into the signal prism, you can see that. Okay. So Now, the important thing about stochastic resonance is when you're detecting it, you actually put the signal you're trying to detect here. All right. Now, it's important that that peak to peak fits within here as well, because if this is really large, it just will act like, actually, it'll act like a non-inverting Schmitt trigger, and you're not really getting stochastic resonance. But in that simulation I just showed you, right, we had 0.2, it was 0.2 sine 2 pi 63 hertz t, right? It was 0.2. The RMS was something around 2.3, right? And that amplitude, that turned that into a sine wave with an amplitude of 3.6. All right. Now, yeah, that 0.2, it's a lot easier to detect. You can decrease this and it'll still detect. And at some point, it can't detect it. All right. Now, that's like the big picture. So if we take this op amp, we don't have a sine wave that we're trying to detect. We're just getting the output noise signature of the noise going through the op amp. And that's what this picture is in the paper. You could think of it as the fast Fourier transform of that. And you have this shape, right? And it's actually a Lorentzian shape, not Gaussian. And then what you do is you kind of say, well, there's the maximum value, there's the minimum, and halfway in between is the full width half maximum. So that's half the maximum. And then this is the width of the frequency. And that frequency is this thing called the Kramer's rate. Now the Kramer's time is 1 over that frequency. And now I have to kind of explain a little bit about that. So if I have these two areas and I have particles in here and they're randomly bouncing around, right? Some will have enough energy to come over, right? And that takes a certain amount of time. Now, because this is random, there's a random time that they pop over, right? And so what we really get is this Kramer's rate is an average. All right. What is it? What is the average time it takes for a particle to jump out of one area and go into another, right? And it's even non-symmetric, where once you go over, you don't come back. So it's like an escape rate. And this is really important in chemical reaction rates and things like that. But it's not a specific time, but it is an average. All right. And that Kramer's time is telling you, well, if I want to detect a sine wave, right, it's best to be near that Kramer's time. You don't have to be exact. In fact, it works. The stochastic resonant works in a wide range, right? But it's telling you if I'm trying to detect 63 megahertz, 63 hertz wave, well, design your system so that the Kramer's rate is at that spot. Now, how do you control that curve? Well, you're actually controlling that curve by increasing the noise. All right. So if I make the amplitude of that noise bigger, the RMS value goes bigger, and it's pushing that curve out. And that's what they've done here. This is 1 over the noise RMS, which they're using this symbol here. All right. That's because the Kramer's rate is supposed to be proportional to this value. And this is, if you saw me drawing that picture, that's the height of the barrier, right? So if I take the log of this, I should get a straight line, all right? And if I'm increasing the noise, the 1 over is getting closer to 1, right? So all I got to do is decrease or increase the noise amplitude, and I can move back and forth, right? So let's say I wanted a Kramer's rate of 1,000. Well, I look here, I hit right, come down, and then that'll give me the noise, the 1 over the noise value of 1.1. So that means I want to increase the amplitude of this signal, right, until I get an RMS of 0.9. So that's how you can design your tuner. All right. So in the project, what you're going to do is run that SPICE simulation and change the value of the noise will stay the same, but you'll increase the magnitude to where it goes plus or minus 0.6, plus or minus 7, plus or minus 9, and so on. Then you measure the RMS, right? And then you measure the full width half maximum. I have a Python tool for that. And then you just make a plot, right? So that's one thing. And that's basically you're measuring the fact that you're measuring the Kramer's rate, but because there's a certain portion where it's linear on a log axis graph, that means this relationship is holding true and you're in a stochastic resonance regime. All right. Now, this is what it will look like somewhat, is that now you've added the sine wave to the Schmitt trigger, right? But maybe the amplitude isn't that great. This is like the original curve with no sine wave added, and now it is, and you're starting to see a peak here. And when the conditions are optimal, you'll see the peak get very large. And then if you take, you know, this is the magnitude, and let's say it's like 2, and then this is the noise without the signal there. What's that? Let's call it 0.05, right? That is the signal to noise ratio, right? And so these plots will come out automatically when you run SPICE, and then you run the Python tool I've set up, okay? And then what can be done is you pick a amplitude of the input sine wave, and they have 0.05, 0.25, and 0.5. And then you change the noise on the input and measure this signal to noise ratio. Right. So that's and then you do it in Scopy, and you do it for real as well. Well, you've got 3 curves here with a lot of data. And so this is when you're going to have to start breaking up the project. Right, well, I'll do that curve, I'll do this curve, you do that curve, and then it all needs to be assembled for one final plot. But, you'll need to have the sample plots of here's, just on the onset of stochastic resonance, here's where it's, in the right regime. Oops. A plot of Kramer's rate versus the noise, right? Of course, you've got to show the definition of full width half maximum. And you got to have your schematic and explain what the hysteresis is. All right. Now, that is a lot of information in a very short time, and you might only caught half of what I said. All right. But what is important is the plots that you have to reproduce. And then once you can do all that, in fact, then you would be ready to work on the research, because there's questions of, can we reduce the power supply? The width of that hysteresis curve, how does it affect the stochastic resonance? What's the fastest signal that we can use stochastic resonance to measure, right? But you've got to be able to repeat the work of these authors before then you can start doing new things. Now, yeah, maybe some of you will be able to start to answer those questions by Friday, but really, if you can repeat somebody's work, that is a major task in any research program, right? And I'm trying to get you to the point where you could do research on this project if you wanted afterwards, right? Another thing, but I know, I don't think everybody got to the Schmitt trigger yet. And tomorrow, we really need to have everybody done with the Schmitt trigger part, so that then you can start working on the project for 2 days, right? And I have to, everything I just said, I have to formally put in the lab manual so you can follow it, all right? But are there any questions before I let you get to work?
Is everything in the lab manual up until this point, up until what you've shared today? And is that all we need, is to just follow the manual to get here?
Eventually, yeah. Eventually, you would just need to follow the manual, right? Looking through and listening to what the TAs said, I don't think everybody finished everything that was in the lab manual just yet. And so today's a catch-up day. All right, so so obviously this is not done yet, right? But here's the actual measurement of a Schmitt trigger, right? That we really need done by tomorrow, so that you can then actually, if you have all that, all you really need to do is add a voltage source here, which is easy in Scopy, and then with the processing that I have with Python, the Python code, you could start recreating those graphs. Okay.
Thank you.
Oh, so yeah, for today, right? I mean, oh yeah, if you want the TA checkpoint, right? Figure 145. If you mean by the goal for today or by tomorrow morning before we start, yeah, I mean that's what, because tomorrow will be chapter 5 and you will see actual content in chapter 5. Okay. Yeah, sorry, I didn't get what you meant right off the bat. So what it is now that you've been working, you can get out of your own way. We don't have to have checkpoints every figure. You know, I'm exaggerating, but anything else? All right, guys. Well, you know what I have to do, which is basically write chapter 5. And I know what you have to do. So we're all working together. Anything else? Okay. All right, guys. Take care.